Hello and welcome to lecture 59 of the course Computational Complexity. This is also the beginning of week 12, and in this week we will see an exciting and interesting topic called interactive proofs, right? So, or in other words, this will help us understand the power of interaction, right? So, to begin, let's consider the verifier model for NP, right? So, we had this verifier model. Whenever X was in the language, there had to be a proof or a witness or a certificate. We use different terminologies. Why? Such that a verifier machine, the verifier is a deterministic polynomial time Turing machine that could verify that X is in the language using the certificate, right? So, for instance, when the language was 3 colorability, the certificate could be a proper 3 coloring. Right. So, whenever the graph is 3 colorable, there exists a proper 3 coloring that could be provided, which can with which it can be verified that the graph is indeed 3 colorable. If the graph was not 3 colorable, whatever colorings you may provide, it cannot be verified that the graph is 3 colorable because the graph is not 3 colorable, right? So, here we have this notion of somebody providing a certificate or a proof that the graph was 3 colorable or a given string X is in the language. So, one question that we could ask is, now somebody is providing us this information. What if it is, so now somebody is just giving us the certificate string. Now, instead of giving it like that, what if we had the capability to hold a conversation with that somebody who is providing us this information? Could we do something more, right? So, instead of just a deterministic polynomial time verifier that just verifies a given X with a given proof Y, what if we could hold a conversation with the person who is providing the certificate, okay? So, this is the main question that the area of interactive proofs ask, right? What if we could have a conversation with the person who provides the proof? So, the person who provides the proof is called prover, right, and the person who is actually sitting and verifying is called the verifier, okay. So, let us try to see, we'll slowly try to understand this and try to develop a model for this, okay, and then we will see various details and based on that various sub models of this of interactive proofs, right. So, the model that we have is, so in the NP we did not ask how we got the proof, right, how the prover got the proof or the certificate, right. If the graph was 3 colorable, somehow magically the prover could give you a certificate which is a proper 3 coloring. If the formula was satisfiable, he will just give an assignment that could be verified, right. So, the prover is considered to be all powerful, and if something needed to be computed, doesn't matter how much time it takes, how much space it takes, whatever, like he is not constrained by any resources, he will just be able to execute the computation, right. The thing is, the prover has this motive that, or may have this motive that he wants you to be convinced that X is in the language, right. So, you are trying to, so his goal is to, by hook or crook, to convince you that X is in the language, right. So, the problem there is that he may resort to dishonest methods to convince you that way, right. So, now the goal of the interactive proof systems is to develop ways where even we have to safeguard ourselves against dishonest provers, but an honest prover and for an X in the language should always be able to convince you that X is in the language. But when X is not in the language, there could be dishonest provers who will try to convince you that X is in the language, but the proof system has to be robust that he should not be able to convince you that way, right. So, and they could hold a conversation. So, now how could that work? Okay, so and the prover is all powerful and the verifier will be bounded. So, we will say the verifier can only do polynomial time computations, okay. So, the model that I have drawn here, so the verifier asks a question Q1, the prover replies A1, okay. So, both of them know the input X, right, both prover and verifier know the input X. They know that the goal is to convince the verifier that X is in the language, right. but the idea of the protocol or the system that we design should be that an honest prover should be able to easily convince the verifier that X is in the language, but a dishonest prover, when X is not in the language, should not be able to convince the prover that X is in the language, right? Or if they try to do that, it should be with limited success. Okay, so both of them know X. So maybe the verifier asks queries Q1 and to which prover responds A1. Okay, so prover just is responding something based on what he knows, which is X, and the query that was asked, right? And then prover again asks another question. So this question could be a function of X and the response that he received in the first query. And then to that query, maybe prover again responds with another A2, which is another response, and this may go on for a while, right? And finally, something like what we had in communication complexity. If the entire transcript is visible to both of them, of course, if the verifier can verify that X is in the language using the entire transcript, right? He need not use the entire thing, but the entire transcript is there available for him to take made use of, right? To be made use of. So if the entire transcript can be used to convince the verifier that X is in the language, he will accept, right? So some things again a bit more formally, the verifier is polynomial time bounded. Okay, he should compute everything in polynomial time. Okay, this also means that the prover cannot send huge messages, or the messages that the prover sends cannot be bigger than polynomially long, right? Polynomially meaning polynomial in the length of the input X, because if he sends a long message that is super polynomial or exponential, the prover does not have enough time to read the responses, right? So the transcript also has to be polynomial length, not just a single message, even the entire transcript has to be polynomially long. Then the prover is all powerful. And as I said, he need not be honest. The goal for him is to simply show that X is not in L. Regardless of whether X was in L or X is not in L, he will try to show that X is in L. Or he may try to show that X is in L. The system has to be able to safeguard against such dishonest provers. And the number of rounds is the number of times they communicate. So here Q1 is the first round, A1 is the second round, Q2 is the third round, A2 is the fourth round, so like that. Okay, I have seen in some places they count two ways communication as one round. So Q1, A1 together form one round, but we will stick to the terminology where one way communication is one round. So what I have marked in this figure, Q1, A1, Q2, A2 together make 4 rounds. Sure. So to begin with, let us consider the case when the verifier is deterministic. Okay. So remember the goal. The goal is to generalize NP, where we just got a certificate and then we are verifying it. So there is no interaction. The prover just gives you a certificate and vanishes. And now it's up to the verifier to do whatever he wants to do with the certificate. But now we are able to have a conversation. So let's say that the prover is deterministic. Okay. So it's called deterministic interactive proofs, or DIP. So we say that a language L has a 2k round, okay, 2k round deterministic interactive proof system if there is a deterministic verifier V. Okay, so the verifier is just a polynomial time Turing machine, and in this case it's a deterministic Turing machine that just looks at the entire input. Okay, so and basically it looks at X and all the responses that the prover gave, right? A1, A2, etc. I am not writing the Q1, Q2 because Q1, Q2 were functions of X and A1. Q1 is a function of X, Q2 is a function of X, A1, etc. So, but then you could make the verifier recompute these functions. So, the deterministic verifier just looks at all of the responses and X, and if X is in the language, the prover should be able to convince that X is in the language, right? So what we say is that there should be a prover that can convince the verifier to accept X, right? So there exists a prover There X is a prover that can convince the verifier that X is in the language. If X is not in the language, no prover should be able to convince the verifier to accept X. So for all provers, verifier should reject X. Right? So it's kind of like the definition of NP, but just that in NP we just had one certificate and that's it. So if X was in the language, there should be a certificate that leads to an acceptance. There X is one certificate. If X is not in the language, whatever certificate you give, it should not be we should not be able to verify that X is in the language. Right? So it's kind of like that, but instead of a static certificate, we have the transcript of an interaction with the prover. Right? That's the only difference. And somewhat, it's not so difficult to see that this model, where it's a deterministic interactive proof, this model is no more powerful than NP. Right? Why is that? Well, so if it's a deterministic verifier, right? So the verifier keeps asking queries, right? So if the prover, so recall that the prover is all powerful. So the prover, if we model the verifier to be a deterministic verifier, right? So this means even the questions that he asks in each of these rounds, all of this are part of the verifier, right? So when the verifier is modeled, all of these queries are also deterministically generated. Now, if the prover knows these, the way the verifier is constructed, the algorithms that go into the verifier, and these are usually no secrets. These are usually not a secret. So in that case, the prover sees X, and he, instead of making the verifier ask the first query, prover could himself ask the first query and output the answer, or and figure out the answer that he would have answered anyway, A1. Then, and because he can figure out the answer, he can also ask the next question that the verifier would have asked, right? Because he knows the algorithm of the verifier, and he can himself produce the next answer, which is A2. Then he can himself, the prover can himself ask Q3. So the prover can himself generate Q1, Q2, Q1, A1, Q2, A2, everything, right? So maybe just to, so prover on his own can generate Q1, A1, Q2, A2, Q3 and so on, and at the end he will just send this entire transcript to the verifier. Look, you would have asked me this, then I asked you this, then I will answer this, then you would have asked me that. So the verifier just has to verify that yes, correct, I would have asked Q1 first. The verifier can verify that. Then now if you gave me A1 as an answer, then I would have asked Q2. That again the verifier can verify, because he would have generated this queries using a deterministic procedure, right? So he can verify that he would have asked Q1 followed by Q2 followed by Q3 and so on. And finally, he can also say that if you had given me all these responses A1 to AK, the verifier would have accepted. So instead of having a conversation, because the prover is all powerful, the prover can himself provide the entire transcript for the verifier to just sit and verify in one shot. So there is no need to have a conversation. Instead, the prover just provides the entire transcript using his unbounded computational power, right? And accepts if the entire, so this is what I said, the verifier just checks if the first query is correct, second query is correct and so on, and finally if the transcript can be verified leading to X being in the language. So if X is in the language, there is an interaction which will lead to a certificate, a transcript, and if X is not in the language, there is no interaction that will convince the verifier, so there is no transcript. So instead of having this conversation, it could just be the prover just giving this one shot transcript, right? So in one shot he could give it, so which is the same as NP, right, where you just give a certificate and the verifier verifies it. So same thing here. So the verifier, so deterministic interactive proofs is just the same as NP. Okay, so we built up so much at the beginning about what if we could have a conversation with the prover and so on. and somewhat disappointingly, it does not really help if the verifier is a deterministic Turing machine. So let us see what else can we do if right in this setup. Is it a useless thing? So let us consider randomized verifiers. Okay, so where the verifier has access to random coins and can generate can execute random algorithms. So all the queries that he generates could be a result of a random process. The final verification could be a result of a random process, could be, so all of this could use random coins. Okay, so the verifier has access to randomness. Okay, so just to give an informal example, which is also there in the Aurora Barak. So let's say that there are some socks. Okay, so let's say red and blue colored socks. Okay, so and let's say I am color blind, which means I cannot tell them apart. I have a red sock and blue sock, and I cannot tell which one is which. Let's say I have red sock in my right hand and blue sock in my left hand. Okay, and let's say the prover is there. Okay, but the prover knows is not color blind, and he can tell the difference between the red and blue. Okay, so prover will say, okay, he will move away, he will not look at me, and what I can do to but then he wants to convince me that these are two colored socks, right? Because I am color blind, I cannot tell whether these two are different colors or the same color. But the prover says he can convince me that these are indeed two different colors. So I am color blind, I cannot really look at these socks and tell that they are the same. So what we will do, so this is an example of how randomness and interaction could together convince the colorblind person that these are two indeed different colors, right? So what we could do is I could just randomly decide to either keep the red at the right and blue at the left, or I could decide to swap them, right? So I will randomly decide to do one of these, and maybe I toss a coin. If it is heads, I will retain them, tails, I will swap them, right? And then I will ask the verifier to prover to come. So prover knows the initial situation, and then he sees, okay, then he can, because he is not colorblind, he will be able to tell, oh yes, you have swapped them, or oh no, you have not swapped them, you have retained them. So the first time we do this, I'll see that if they are indeed two different colored socks, he will be able to correctly say that I have swapped them or not. But if I repeat it, let's say 10 times, and if he gets it right all the 10 times, then I will probably be convinced. How can he be able to say correctly each of these 10 times, right? Whereas if they were both the same colored socks, let's say they were both blue, then he would not be able to tell them apart regardless of whether I swapped them or not. So it's like a random thing. So I will just swap them or not randomly, and he has to tell me if I have swapped. But then there is no indicator for him to decide whether I have swapped them or not, right? Both of them are blue. So the best he can do is just simply guess something. But whatever he does, he will be right with probability half, right? Because I may have or may not have swapped them. So the prover is powerful because I have the limitation of being colorblind, but the prover does not have that limitation, right? So that is the separation of powers that the prover and verifier have, right? So this is an example of a protocol that the prover and verifier can together execute. So the same thing we will exactly the same idea. Okay, so there's nothing more fancy, but we will use it to address a problem called graph non-isomorphism. In fact, we have seen a similar or a related problem called graph isomorphism in lecture 22 as a candidate problem, which was NP intermediate. I think we saw it in the context of Ladner's theorem. So what are graph isomorphism? Isomorphism is two graphs. Right? So the problem instance contains two graphs which are isomorphic. Graph non-isomorphism is a complement. Two graphs that are not isomorphic. What do we mean by isomorphism? Isomorphic? It is just the same graph drawn differently or relabeled or whatever. Or if you'd like to think in terms of matrices, let's say take the adjacency matrix, let's say you permute them in some way, the rows in some way and columns in the same way. So you get it's like a relabeling of the vertices. So just to give an example, so here I have two graphs. By the right side, 1, 2, 3, 4 is a graph and A, B, C, D are the vertices of another graph. But if you look at them closely, they are isomorphic. So 1 may be mapped to C, 2 may be mapped to D. Okay, so maybe I'll just write 1 may be mapped to C. Maybe I'll just write them by the side. 1 to C, 2 to D, 3 to B and 4 to A. So you can see that here 3 and 4 are adjacent, so B and A are adjacent, C and B are adjacent, so 1 and 3 are adjacent. So you can verify that they are just the same graph relabeled and maybe redrawn in a different way. So the question is, if I give two graphs, are they not isomorphic? So because it's an asymmetric, it's not really so we'll look at graph non-isomorphism. So are the given two graphs not isomorphic? So these two graphs are isomorphic, right? So we can do exactly the same thing that I said in the case of SOCs. Okay. So before that, what is a trivial algorithm for graph isomorphism? Trivial deterministic algorithm. So suppose they are both n vertex graphs. So if one of them is n vertex and one of them is, let's say, n plus 1 vertex graph, then they are clearly not isomorphic, right? Because the number of vertices itself do not match. So the issue arises only when they have the same number of vertices. So suppose both of them have n vertices. The one easy thing to do could be to try to generate all possible relabelings of one of the graphs and see if any of these relabelings match the other graph exactly. But there are n vertices, so there are n factorial, potentially n factorial mini relabelings for one of them, and that is a lot of relabelings to test. Right? So that is why it is not in deterministic polynomial time. But graph isomorphism is in NP because if you give me two isomorphic graphs, I can give you a certificate. So I can tell you which relabeling maps G0 to G1. So graph isomorphism is in NP. Consequently, graph non-isomorphism is in co-NP. Right? But here we are looking, so graph isomorphism is in NP. So clearly you can also do graph isomorphism in interactive proofs. Right? So the prover could just give the certificate. But what is interesting is that graph non-isomorphism, we can't seem to think of a certificate that tells you that these are different. But there is a proof system, interactive proof system, where the prover will be able to convince the verifier that the graphs are not isomorphic. So we do the exact same thing as we did in the case of SOCs. The verifier picks a random 0-1 bit, right? And he picks a permutation, which is a relabeling of the vertices. And if he got 0, if B is 0, then he will permute G0 with the permutation that he got. If he got B equal to 1, then he will permute G1. Okay, and the resulting graph of the permutation. So the permutation, the resulting graph is H. Notice that H is a result of both choices, the random bit and the permutation, random permutation, because he permutes G0 or G1 based on whether B equal to 0 or 1, and the permutation is done on the basis of the random permutation. And the resulting graph is called H. So H, maybe just to be concrete, H is equal to sigma of GB. H is sent to the prover. Okay, and the prover is all powerful. Now, because he is all powerful, he is not computationally restricted. He could look at H, he could try out whatever he wants, and if G0 and G1 are indeed different graphs, right? He could try out various things with H and see which one it came from. But if G0 and G1 are indeed isomorphic graphs, H could have come from either of them. There is no way that the prover could tell where it came from, because he does not know the random choice, the B and the permutation. So it could be a scrambled form of G0 or scrambled form of G1, because they are both the same thing. If you relabel G0 in some way, you get G1. So you scramble G0 in some way, you scramble G1 in some other way, you could end up with the same graph. So there is nothing that the prover can do if they are the same graph, except randomly guess that B equal to 0 or something, or B equal to 1 of them. So, and the verifier will accept. So verifier is expecting the prover to tell where the graph came from. Did H come from G0 or G1? If the prover can correctly say this 0 or 1 each time, then the verifier will accept, right? If not, he will reject. Okay, so so clearly, if the graphs are not isomorphic, as I said, then verifier can tell you, because he can, just like the colorblind case, he could distinguish in the non-isomorphic case, he can distinguish. But if they are the same, graph, right? If they are isomorphic, so notice that the non-isomorphic case is a yes instance for the language graph non-isomorphism, and the isomorphic case is a no instance, right? So he cannot, in the case of isomorphic case, he cannot do better than half. So if it's a yes instance, he will make sure that the verifier accepts with probability 1, right? Because he will always be able to correctly output the answer. If it is isomorphic, the best he can do is half. So the best prover, whatever you try to do with the prover, the best one can do is half. So there is a distinction here, right? So the probability of acceptance by the verifier, given whatever the prover could do. If it's a yes instance, there is a prover that can make him accept with probability 1. If it's a no instance, whatever the prover does, whichever prover it is, the best he can do is half. So there is a gap between the yes instance and no instance. And notice that here we use the fact that the choice of B, the random bit, and the choice of the permutation were both withheld to the prover. They were not provided to the prover. So the random choices made by the verifier were private. They were not told to the prover. So note, this is a very important aspect of this proof. If either B or sigma was revealed to the prover, then the prover could immediately tell where it came from. So this is an example of an interactive proof for graph non-isomorphism, and clearly, as I said, graph isomorphism already has an interactive proof. So this is an example of a language which is not known to be in NP. Graph non-isomorphism is in co-NP, and we don't know if it is in NP yet, but we have an interactive proof. So this already indicates that the class of languages that have interactive proof systems seems to be more powerful than NP, because we don't have we don't know whether graph non-isomorphism is in NP. So just to formalize the setup of interactive proof systems, again we have verifier and prover. The prover asks, so the verifier poses queries 1, Q1, Q2, Q3, and the prover provides responses A1, A2, A3. Right. So Q1 is the verifier's first query using X and random string, the random input. So the random input, you could think of it as maybe a long random input, and verifier using different chunks of it each round. Some response comes back, A1. Q2 is depends on the input X, the random string R, the first query Q1, and the first response A1, and so on. Right. and at the end, based on the entire transcript, it is decided to accept or reject. So we say that a language L is an IPK. Okay, so what is IPK? IPK is the interactive proofs of k rounds. If there is a probabilistic polynomial time machine V, okay, so we are not going to talk about deterministic verifiers. From now on, everything is going to be probabilistic or randomized verifiers V that has a k round interaction with a prover P, such that if X is in the language, there is a prover that can convince the verifier to accept with probability at least 2/3. And if X is not in the language, any prover that you can think of can convince the verifier to accept with probability at most 1/3. So the first part is called completeness and the second part is called soundness. So completeness corresponds to when X is in the language, soundness corresponds to when X is not in the language. So there is a probabilistic polynomial time verifier V that has a k round interaction with the prover, such that when X is in the language, the prover makes the verifier accepts. There is a prover that can make the verifier accept with probability at least 2/3. And when X is in the not in the language, so when X is in the language, there is a prover that can convince the verifier to accept with probability at least 2/3. And when X is not in the language, any prover, the best they can do is to convince the verifier with the probability at most 1/3 to accept the string X. And we will, when we say IP without, so I said L is equal to IPK for a k round interaction. When we simply say IP without a k associated with it, this indicates IP of polynomial number of rounds. So they can have potentially polynomial many rounds of communication, right? And what we have seen so far is that graph non isomorphism is in IP2 because there was 2 rounds of communication. The verifier conveying the random bit, the permuted graph H, and the prover conveying the purported random bit or the random bit that he thinks was used, right? So 2 rounds. Okay. Some comments so far, some remarks. Right. So we'll close this lecture with these remarks. So first of all, this was a generalization of NP, which should not be that difficult to see because instead of verifier or the prover just giving a certificate, now there is an interaction going on. So and we saw deterministic IP is equal to NP. Randomized has more power. So there is something that the NP is contained in IP, right? Because a language in NP, the prover could just give the certificate and make the verifier verify, right? That's one proof system. Another thing, BPP is also in IP, right? Because the verifier himself has the ability to use random coins. So he could just disregard the prover and do everything himself, and this will be a BPP machine, right? So if the verifier just ignores the prover, he is like operating as a BPP machine. If the verifier just ignores randomness, it is like deterministic interactive proof, which is NP, right? So both NP and BPP are subclasses of IP, interactive proofs, and another way to say it is that interactive proofs generalizes both of these, right? And like in BPP, we could improve the probability, so that nothing is special about 2/3 and 1/3. We could improve this probability to very close to 1 and very close to 0. So one example is 1 minus 1 divided by 2 power m and 1 divided by 2 power m. So you could make them exponentially close to 1 and 0 respectively. So by exactly the same argument as BPP boosting, we can do multiple rounds of this. So you do 1 round, you do 2 rounds, you do 3 rounds, and take the majority, whichever one it comes. Right? Exactly the same arguments are not bound. Everything goes through. Right? One small point which I will state, but which actually requires a very sophisticated proof, is that whatever I just described is a serial process, and this can be made into a parallel process also. Now two points, or one point rather. So we said that the verifier, when we moved from a deterministic verifier to a randomized verifier, the capability is increased, right? So deterministic verifier was NP, but randomized verifier seems to be able to do more things. What if we made the prover also randomized, or what if the prover was able to do probabilistic stuff? Well, this doesn't really help, because as it is, the prover is considered all powerful. So as we know, BPP is contained in sigma 2, for instance. So there is which means there is a higher class of non-randomized machine that can do whatever BPP does. So there is nothing much to be gained, or in other words, if there are multiple options available to him, and if the prover is executing a random protocol, then because he is all powerful, he can also see the best possible out of the many things that he does, right? So he can always choose the best option, best random coin. So there is no benefit gained by making the prover randomized. Another point is that the entire transcript is a polynomial. There are polynomially many rounds, and then each round has polynomially long transcript. So the entire transcript is of polynomial sized, right? And the verifier can just verify that this corresponds to something, a proper proof or not, right? So suppose there was no prover, right? Suppose the verifier had to do the work of the prover. So in other words, how powerful can the prover be, beyond which it doesn't really help? The answer is, we can replace the prover by a p-space bounded machine, p-space machine, because so the prover can see what is the best way to convince the verifier by just going through all the possible transcripts. In other words, another way to look at it is that if a language is accepted because of this interaction, we can just, another way to decide the same language is to just try out all the possible transcripts, and all the possible transcripts is of polynomial size. So I can try out all the possible polynomially long transcripts and check that this is a valid transcript, and then accept or not accept X based on all of this. And this process requires only polynomial space, because the size of the transcript is polynomial. So the entire process, this entire if a language has an interactive proof, this language also has a can also be decided in p-space, right? So this is another point. Now there are two further points that I would like to state. One is perfect completeness, which means recall that completeness is the case when X is in the language. So we said that the probability of acceptance of X should be at least 2/3. And we already saw that 2/3 can be pushed very close to 1. Can we push it to exactly 1? And the answer turns out to be yes. Using some ideas similar to the proof that BPP was in sigma 2, and appropriately modifying the verifier, we can make perfect completeness, meaning the completeness part here, this probability 2/3, this can be pushed to 1, right? So perfect completeness, so any interactive proof you can replace with an interactive proof of perfect completeness, right? And the next thing is perfect soundness. So soundness is the situation where X is not in the language. So can we push the probability of acceptance when X is not in the language from 1/3 down to 0? We already saw that we could make it exponentially close to 0, 1 by 2 power something. Can we push it to 0? And this turns out to be, this looks unlikely. We do not know how to do that. Because if we have perfect soundness and perfect completeness, this is like a deterministic interactive proof system, which we already know is equal to NP. So unless the entire class of IP is equal to NP, perfect soundness will not be possible. Okay. Finally, one more point. We used private coins for the protocol where for graph non-isomorphism, right? Meaning it was important that the random bit B and the permutation sigma were withheld from the prover. That protocol would not have worked if this had to be made public. This had to be told to the prover. So can we have interactive proofs where the random coins are public, right? So this, one may think that this weakens the entire system, because the key power in the graph non-isomorphism protocol came from the fact that some information was hidden from the prover, the random coins, right? The prover is all powerful, but he does not know the random coins, right? Because he can do any computation, but there is some input, the random coin, that he did not know, right? So when we insist that the random coin should be made public, we may think that the prover will lose some power, or the proof system may not be able to do some things. So interestingly, it can be shown that whenever there is a private coin protocol, you can get a public coin protocol, sometimes with a bit more rounds, but whenever there is a private coin protocol, you can also get a public coin protocol. So protocols with public coin proof system are as powerful as those with private coin proof system. So this is a slightly interesting, somewhat surprising fact, right? And some small notations, and before I conclude this lecture. The private coin setup is called IP, as we defined already, right? And the public coin model is called AM. It's short for Arthur Merlin. So I'll explain when we talk about AM. And there is one small interesting fact, is that when I say IP without any number of rounds specified, the implicit what I want to say is that it stands for IP with polynomially many rounds, right? But when one says AM, what they imply, what they want to say is AM with 2 rounds. Prover sends something, verifier sends something, 2 rounds. So this is a bit of an inconsistency with the notation, but then that seems to be the standard thing that people are following, right? Inconsistent notation. But unfortunately, this seems to be the standard. So we'll have to just get used to this, right? And so in the coming few lectures, we will see IP, how powerful IP is. We already saw that IP can do some things that possibly are not there in NP. We already saw that IP is contained in P space, so it's not more powerful than P space, but how far powerful it is, right? We will actually see that IP is as powerful as P space, or I will at least mention that. And then we will see different aspects, like how different aspects about in public coin and private coin protocols, how they relate to each other, and how sometimes interactive proof systems have also been used to infer something about other aspects of complexity, right? We'll derive at least one statement which has nothing to do with interactive proofs, but proved using the interactive proof systems. And yeah, so that in this lecture we just defined interactive proof system. We formally defined it, and we saw deterministic interactive proofs, the interactive proofs where the verifier can be randomized, and then we saw a bunch of remarks, and that's all I want to say. Thank you.